There we go. So we enter in the number of absences into L1, and then we enter in the corresponding final grades into L2. Eight, 90, and 78. So once you have those entered, just hit second mode. So that'll take you back to the home screen. Then go into stat, calculate, and then go to line reg a plus bx. So that's just linear regression with a plus bx is the form where a is going to be the y-intercept and b will be the slope. So tap that, and then it'll say what's going to be the x list in this case. So x is going to be the number of absences, so that's an L1. And then where is the y list? So the y list is going to be our final grades, and that's an L2. And frequency list, don't worry about that. You could store your regression equation in, say, for instance, if you want to draw a line actually on the calculator, you can store it in one of these y variables. So there's like y1, y2, y3. And for mine, it has different colors, but for yours, it may not. But we're not going to worry about storing it. So then you just hit calculate. So it tells you the A and the B. I hit the wrong thing. That's just telling you what the coefficients for that will be. You'll actually need this part later. Let's see. There it is. So linear regression t-test, number F on tests. That's what we want. So then you tell it where x and y are. So x is in L1, y is in L2. Frequency 1, beta and rho, just leave that as equal. That's just saying what's the alternative hypothesis in this case. See if that's it. Is that the right one? Yep, it is. Okay. So then if you scroll down, it'll tell you what the value of R is. So R in this case is negative 0.944. So since it is strongly negative, so we have R is equal to negative 0.944. So we can conclude there is a strong negative linear relationship between number of absences and your final grade. Okay, so it also tells you the values for A and B in this case, so the value of the y-intercept and the value of the slope. So if I asked you to compute what is the predicted final grade for someone who has like 8 absences, you can plug that into the formula, and it will give you the corresponding predicted final grade. Does that kind of make sense? Okay. So the sample correlation coefficient R can be used as an estimator of the population correlation coefficient rho. So rho just looks weird. It's just basically a Greek P. So you can actually perform a hypothesis test on this correlation coefficient to see if it's not 0. So basically, if exists a linear relationship between the two variables. So that's what we're going to do here. And again, you can do it on your calculator, just like I did there. So again, assumptions must be made. So the data is quantitative and obtained for a random sample. So if it wasn't quantitative, that doesn't make sense to make a scatter plot, really. So that's why. The scatter plot must show that the data are approximately linearly related, so there exists a linear relationship between the two. There are no major outliers in the data set, so there are no points that are like crazy far away from the line. And then the variables x and y are from normally distributed populations, so it just means they're normally distributed. Okay, so what would the hypothesis look like in this case? So the null hypothesis is going to be that our population correlation coefficient is equal to 0. So that means under the null hypothesis, there is no linear relationship. So if the null hypothesis is there's no linear relationship, what will the alternative be? Obviously the opposite of that. So in this case, it would be rho is not equal to 0. So that would mean there exists a linear relationship. That's kind of self-explanatory, right? Just the opposite of it. So where do these critical values come from that we're going to use, and how do we get the corresponding p-values? So the p-values you don't need to really worry about. Your calculator will calculate them for you if you run the linear regression t-test. So it will tell you the corresponding p-value and the test statistic. But the test statistic is just kind of useless in this case, so there's a lot easier way to do it, but we'll actually cover that next. So let's go through how we did it in chapters 8 and 9. So where do the critical values come from? It's just from your t-table. So you use the corresponding degrees of freedom and the alpha value, and you should be able to find the critical value from that. So where do the critical values come from, and the p-values? The t-table. Okay, let's do something real quick. What the? You. I don't know how in the world, but I just drug the thing all the way off the screen and I didn't mean to. The heck? Come on. I don't know how in the world that happened. Okay, I'm gonna do something real quick. Sorry, everyone, my computer had a little whoops in the room. So I had to switch browsers. So now we're back. We're 2 and 4 on this page. Oh, on this page, 2 was the scatter plot must show an approximately linear relationship, and 4, the variables x and y both come from normally distributed populations. Okay, so There we go. That's what I want. And drag that one that way. Okay, so let's get back on track now that that mishap is concluded. So this means the same decision rules apply as what we had in chapters 8 and 9. So we are going to reject the null hypothesis if the t-test statistic we compute is greater than the positive t alpha over 2, or if it's less than the negative t alpha over 2. And does everyone know why there are two critical regions? Because the alternative is not equal to, so there's going to be a lower one and an upper one. So that's why there's two critical values there. So and then the p-value method is always reject the null hypothesis if the p-value you get is less than or equal to the corresponding alpha that the problem gives you. So what does this test statistic look like? So this one's a little different than what we've had before. So t-test is equal to the sample correlation coefficient R times the square root of n minus 2 over 1 minus R squared. So in here, instead of having a degrees of freedom of n minus 1, the degrees of freedom when we're doing this t-test is n minus 2. So it's a little different. It's just off by one number. So just how we calculated t-test statistics before and compared them to critical values, you can do the same thing here. So look at the example we just did. So we found out that R was equal to negative 0.944. So then using that information, we can do a hypothesis test on whether the population correlation coefficient is equal to 0 or not. So the first step we have, just like we did in chapters 8 and 9, is identify the two hypotheses. So in this case, the null is rho is equal to 0, and the alternative is rho not equal to 0. So the decision rule So since we're doing a traditional method, so this is just a critical value approach, we're going to reject the null hypothesis if the t-test statistic we compute is less than the negative t alpha, or if it's greater than the positive t alpha over 2. So how are we going to find these critical values? So you have your t-table. So what we need is the corresponding degrees of freedom. So the degrees of freedom we had in that case. So how many people did we sample? So if we go back to here, we had 1, 2, 3, 4, 5, 6, 7. So 7 minus 2 will be our degrees of freedom. So the degrees of freedom then is equal to 5. And we're testing it at alpha equals 0.05. So it's alpha is 0.05, and we have 2 tails because it's not equal to. So then looking at our t-table, we need to go to the degrees of freedom is 5. Alpha is equal to 0.05 with 2 tails, and that'll be 2.571. So that means this negative t alpha over 2 is negative 2.571, and the positive is 2.571. So the next thing we want to do is compute the test statistic. So on your final exam, if I have one of these, it'll be set up just like this. So, but it'll be multiple choice, so you get to pick which one you think it is. So it'll be a little bit easier. So the test statistic we compute is t-test is equal to the sample correlation coefficient r times the square root of n minus 2 over 1 minus r squared. So we have r, we found earlier. How do we get r squared? You just take that number and square it. So doing that, we have that negative 0.944 times the square root of 7 minus 2 divided by 1 minus negative 0.944 squared. So be careful when you're squaring a negative number. So in this case, since our r is negative 0.944, we want to make sure we include the parentheses around that negative. So whenever we square it, it becomes positive. So if I work out that, I end up with negative 6.4. So then, using this t-test statistic and comparing it to the critical values, I can come to a decision. So based on that t-test statistic and comparing it to the critical values, what should we do? Yeah, reject it. So reject the null hypothesis because the t-test statistic we computed is less than negative t alpha. Does everyone see why that is? Because negative 6.4 is obviously more negative than 2.571. So that means it's less than it. So this leads us to conclude there is a significant linear relationship between number of absences, I'll just put number of ABS, and final grades. So is everyone okay with how we did that? Just doing the same stuff we did in chapters 8 and 9. It's just the way we compute the test statistic is slightly different. So it's the same thing we've been doing all along, just different formula. So you could also doing it using the p-value method. Okay, so what we want to do is see where does this test statistic fall between what two alpha values. So in this case, we have the degrees of freedom is equal to 5, and we're seeing is there any range of these two alpha values right here that this falls in between. So we calculate our test statistic was negative 6.4, and obviously the highest critical value is 4.032, and that corresponds to a alpha with two tails of 0.01. So that means that our p-value is less than 0.01, and obviously If it's less than 0.01, it's less than 0.05. So we would reject the null hypothesis since the p-value is less than or equal to alpha, and that will give you the same conclusion as above. Do you want me to write that down? I don't care. It'll be posted later today, probably. See if anyone said anything in the chat. Nope. Okay, so when I was looking for exam questions, I was debating whether putting one of them on there that you have to find the corresponding range of p-values. If I give you a t-test statistic and tell you whether it's one-tailed or two-tailed, do you think you could do that or not? Okay. I was looking through old exam questions that I've seen, and I was wondering if I should put it on there or not. So we could also take another approach to this, and it's a lot easier than what the last one we did is. So, also note there's no confidence interval method here. So we're just going to do the critical value method, basically. So, a little fun fact, I didn't do it for chapters 8 and 9, but all of those hypothesis tests you've been doing, you can do in your calculator. Just let you know. You just have to enter in the data and go to calculate and then run whatever t-test or z-test you want. I didn't think about that until now, when I just did it on the calculator. But that's how you do it, guys. So we can do another approach here. So we can use table I in your little packet booklet, or whatever it's called, the last page. Yeah, it's table I. And it says critical values for PPCM. So I don't know what PPCM means. I'm assuming Pearson something. So that's where we're going to find these critical values. So this right here is going to be the highest value of, I guess this is R in this case, that would indicate a not a significant linear relationship between the two. So it's going to depend on the alpha value and the corresponding degrees of freedom. So, and again, it says up here, note the degrees of freedom is equal to n minus 2, and we're doing a two-tailed test. So, the table shows the values of the correlation coefficient that are significant for a specific alpha level, given a specific number of degrees of freedom. Sorry, that was gross. I had Carl's Jr. before I came. It was yummy. I had biscuits and gravy. So, the null hypothesis is the same thing. So, rho is equal to 0, and the alternative being rho is not equal to 0. So, on the final exam, I will literally put what is the null hypothesis, and you will select from one of the 4 answers. Easy enough? Okay, and remember, the null hypothesis is always, there's an equal sign in it. So if I see any less than or greater than in the final exam, I will lose my mind. Cool? Okay, so we've got the null and the alternative hypothesis. So I can't remember if I've been writing H1 or HA. It means the same thing. It just means the alternative. Sorry, I'm a graduate student and we use both. Just depends on what class you're taking. So, and the decision rule, will be reject null hypothesis if the sample correlation coefficient R is greater than 0.754. And I'll show you how I got that in a second. So the way I got that was, so the degrees of freedom we had in this case was 7 minus 2 n minus 2, which is 5. So we have a degrees of freedom of 5, and alpha is equal to 0.05. So then we use this table I to find what's the largest correlation coefficient that is not significant. So the degrees of freedom of being 5, and alpha is 0.05, so 0.754. So we reject the null hypothesis if our sample correlation coefficient is greater than 0.754. You could also say if the magnitude of your correlation coefficient, because you can take the absolute value. So then part 3 is the test statistic. So in this case, that will be, we have that R is equal to negative 0.944. So that means the absolute value of R is equal to what? Does everyone remember what you do with the absolute value? It just takes the negative off there. So the absolute value is the distance a point is away from 0 in the positive or negative direction. So if it's negative 0.944, it's obviously 0.944 away from 0. So that means the absolute value of R is equal to is the positive 0.944. So then taking this and then using our decision rule, we can come to a conclusion. So the decision in this case is what? The same thing as it was before. Reject the hoe because the absolute value of R is greater than 0.754. Simple as that. So that's the easier way to do it. So, and you'd have the same conclusion as you did on the previous page, that there exists a significant linear relationship between the number of absences and the corresponding final grades. Is everyone following me up to there? So, I believe that is all for section 10.1. So section 10.2 is about regression. So in the first section, we discussed how to draw a scatter plot of two quantitative variables, and that would help us to determine if there is a linear relationship or not, and how to conduct the corresponding hypothesis test. Gosh dang, why do I keep getting potential spam calls? So if a linear relationship is present, the correlation coefficient is calculated, and we are able to test the significance of the linear relationship. So if the correlation coefficient is significant, so if it's significant, what does that mean about the null hypothesis? So that means we rejected the null hypothesis. And we can now determine the equation of what we will call the regression line. So why would we want to determine the regression line? So like I said earlier, it's to make predictions. So say, for instance, you want to find the predicted final grade for someone who has a certain number of absences. You can do that based on the regression line. So you just plug in the value of X, and it will give you the corresponding output for the value of Y. So why would we do that? So researchers are able to make predictions and estimations based on the trend of the data. So based on the regression line. Does that make sense? So it's using the line basically. So in like college algebra, if you ever took it, whenever you were given an equation like y equals mx plus b, and you were given a certain value of x, you could plug it into the formula to find the corresponding y. That is the same thing we're doing here. So it's just we used sample data to find the corresponding m and b in this case. So in this case, it'll be, we call it a and b. So a is the y-intercept, b is the slope. So, like we said, have many of you heard of the line of best fit? And it's probably from college algebra or wherever the heck you found it. So, the line of best fit that they use in there is equal to y is equal to mx plus b. So, as many of you should know, m is the slope, b is the y-intercept. So, do any of you know what that y-intercept actually means? So in this case, the y-intercept would be, what is the corresponding final grade with a student who has never missed class? So they have 0 absences. So that's what it is. So the regression line is similar to the line of best fit. We just use different symbols. So the regression line we're going to make is what is going to minimize the sum of the residuals. The residual sum of squares, actually. So it literally takes a box around the like this thing right here. It creates a box around that residual, and we're trying to minimize the area of all those boxes. So that's what this does. That's what your calculator is doing when it actually calculates those values of A and B. So, and then what the correlation or the R squared, which is the coefficient of determination. So you just take the R value and you square it. So what that will tell you is the proportion of variability explained by that line. So we'll talk about that later. So the distance between the actual value, so the actual value will be the observed value. So say this observed value right here, we're going to call it y. And the predicted value, y hat, or you call y prime in this case. So here is our predicted value, y prime. Here's the actual value, y. Then the distance between the two is what? It's called the residual. So, and that is represented by D1 through D7 on the graph above. So we have observed values, and then we have the predicted values, and the corresponding distance between the two is the corresponding residual for that point. So does that make sense? Okay. So these values are used to determine the line that best describes the linear relationship between the two variables. And to do this, we want to make these residuals as small as possible. So we use something called least squares estimation to do this. So to create the linear regression, or the regression line, you can call it line of best fit or whatever you want to call it. We take the sum of the squares of the vertical distances from each point to the line at a minimum. So what we want to do is basically what I just said. You want to minimize the sum of squares of the residuals. So then we can come up with a formula to find these corresponding values of A and B that will do such. So how do we write the regression line? Why do people keep calling me? Leave me alone. So you could call it y prime. You could also put y hat. Y hat is prediction as well. So that's going to be equal to a plus b x. So that's going to be the form of the regression line we're going to look at in this class. So where we have the y-intercept is given by, what do you think? So in this case, the y-intercept is given by a. And how do we calculate a? So there's a nasty formula. So we're going to take the sum of all the y values. We're going to take the sum of the x values squared. We're going to subtract off the sum of the x's times the sum of the y's. And then we're going to divide by n times the sum of the x's squared minus the sum of the x's at quantity squared. So, do you want to memorize that formula? The answer is no, obviously. So, and then there's also a formula for b. So, b in this case is the slope. So, the way it calculates that is equal to n times the sum of the x, y product. So it takes each x and y, multiplies them, and then adds them, minus the sum of the x's times the sum of the y's, and then divides by the same denominator as above. So that's n times the sum of the x squared minus the corresponding sum of the x's, that quantity squared. So that's how you would find it if I wanted you to use that formula, and that's not going to be fun because I don't even think your calculator gives you the sum of the y's and the sum of the x's. Or it gives you the sum of the x's and the x squareds, but it doesn't give you the sum of the y's. So how are we going to do this? You're going to use your calculator. It's going to be easier. So the way you do it in your calculator, so how we had it earlier was, so we had our number of absences in L1. We had the corresponding final grades in L2. So then I'm going to go back to the home screen, hit stat. What is this? LN? Oh, that's So if you just want to find the values of A and B, you can go to calculate linreg, so that's number 8. And you just tell it where your x's and y's are. So once you do that, just hit calculate. And it will tell you the corresponding A, which is your y-intercept, and B, the slope. So in this case, we have the prediction line equation is given by y prime is equal to 102.49 minus 3.62 x. So that will tell you the linear regression line. So then you can use this linear regression line to make predictions. So a little note, the sign of the correlation coefficient will always be the same as the sign of the what do you think. So the correlation coefficient tells you the strength of the linear relationship between the two variables, and the sign tells you whether it's negative or positive. So it tells you the direction of the linear relationship, so whether it goes positive, so it has an upward slope, or it's negative and has a downward slope. So the sign will match the sign of the slope of the regression line. So is that true for our example? So we had that R, the sample correlation coefficient, was equal to, so R was equal to negative 0.944, and our slope, B in this case, we had B was equal to negative 3.62, and obviously both of these are negative. So yes, it matches up. Is that kind of obvious? Does everyone understand why that is? I would take your silence as a yes. So the regression line can be used to make predictions for the dependent variable. So we're going to give you a specific input x, and we're going to ask for an output of the prediction y. So you should use these guidelines when you are making predictions. So the points of the scatter plot fit the regression line reasonably well. So that just means the linear relationship is somewhat strong. The R value that we calculate is significant. So based on that hypothesis test method, you can actually calculate that that sample correlation coefficient is significant based on the degrees of freedom and the specified alpha. So if R is significant, then what does that mean we did for that hypothesis test? It just means we rejected that hoe. We rejected the hypothesis, all it means. So the value of a specific x is not much beyond the observed values in the data set. So if we have a range of data values, say from like 0 to 10, then the values of x we want to actually try to plug into that formula to make a prediction should be in between 0 and 10. Because if we try to predict something that's not within our data set, so if it's far out, we may not get an accurate prediction because we didn't have an actual observed value for that given x. Does that make sense? Okay. So if R is not significant, then the best predicted value for a specific x is what? What do you think? Is the mean of the y values. So say, for instance, if there is not a linear relationship between the two or a significant one, then our best estimate of what y is for any value in the data set will be the mean of the y's. So let's go back to our example and estimate a couple things. So use the equation of the regression line to predict the final grade of a student that has 4 absences. So remember we had the regression line equation was y prime is equal to 102.49 minus 3.62x. So in this case, what are we plugging in as x? So we're plugging in x equals 4. In this case, so whenever we plug in x equals 4, that gives us 102.49 minus 3.62 times 4. Easy enough, right? So once you do that, you end up with 88.01. So if a student has 4 absences, their predicted final grade will be an 88.01. So do you think that is actually accurate in this class? I would say no. There are some people that I've never seen in class that have good grades. So now, what is the predicted final grade if a student has 20 absences? So you just do the same thing. So you have y prime is still the same regression equation, 102.49 minus 3.62 times x, but in this case, x is 20. So that is equal to a 30.09. So that student would be sad. So the next thing we want to ask ourselves, can we actually predict what the final grade that someone with 20 absences will have? So we need to look at what was the highest number of absences in our data set. So it was 15. So there could be some possible what they call extrapolation there. So we're trying to estimate a value that is not within our estimation power, I guess you could say. Does that make sense? We're estimating something that's too far beyond what we actually observed. So we'll take a little break here, probably like 5 minutes or so, and then we'll continue on. So I'll just tell them what I just said. So that's all I said. So note that we are making a prediction beyond the scope of the study. So you must be very careful when making these predictions because they can lead to extrapolation. So extrapolation is basically you're asking a question that you're not supposed to ask because it's beyond the scope of the study. People online, I kind of didn't notice I was muted after I started. So I guess that is all we will do for today. Next time we will finish section 10.3 and begin on reviewing for your final exam. If you want to do well on the final exam, I would highly encourage you to come to class. If you do bad on the final exam and you don't come to class, I don't care. So that's my philosophy towards it. If y'all need any help, email me or anything. Other than that, I will see you on Thursday.